This is Mr. Weideman, AP Physics, Lafayette High School, working on our AP UT Quest assignment on working energy. We've got a problem here called engine power, where we're dealing with the vehicle moving along at constant velocity, and then all of a sudden it starts going up a hill, and it wants to find out the speed of the car on the hill. Okay, the key elements are going to be the power is constant. So whether I'm moving up a hill or not, I'm using all the power available. So if we've got this vehicle going on a flat road, it's top end speed, power is maxed out, and then I start going up a hill, then the car's going to slow down. Some of that kinetic energy has to be traded off for potential energy. As I start climbing up the hill, I'm gaining potential energy. That means I have to lose kinetic energy because I don't have any more power available. Okay, so all that power is not only going into kinetic energy, it's also going into potential energy. All right, also this constant speed thing, that tells us that at least when I'm on the flat, and again when I'm up the incline, I can assume equilibrium. So what that allows us to do is we can use our power equation, force times velocity, and we can back calculate then these dissipative forces that are acting on the car. Now, the dissipated forces are in equilibrium with the applied force, and that is going to be a constant for the next part of the problem. But what we can see is going to happen here is that as I start climbing up the hill, not only am I going to have the dissipative forces to overcome, but I'm also going to start lifting up the weight of the car some. So what does that mean? Then that means that my applied force has to go up. Therefore, my velocity has to go down because my power is going to be constant. So let's back calculate this dissipative force, 2850 newtons. That's going to be there regardless of whether we're going up an incline or not. All right, so now let's take that information and let's move on up the incline. All right, so how is that going to change my free body diagram? Well, what's going to happen here now is I have to consider I have an element or a component of my weight that my applied force has to overcome. So what's going to happen is I need more applied force because the applied force has to overcome these dissipative forces of friction plus this component of weight. Now I can figure out my new applied force. Again, I know my power output is constant, so I can calculate my new velocity. Let's set that up. All right, power is a constant. I've got those dissipative forces. And then I also have to overcome a component of my weight that's working against that applied force. And then that's going to give me my new velocity. I've already calculated the dissipative forces. The weight is given. So now then I can just calculate my velocity. We worked everything in standard units. We had to. Because that weight term is in kilograms meters per second squared. So that really means I had to convert everything to standard units. So then when I got my standard units in meters per second, I believe the Quest problem says it wants the final answer in kilometers per hour. So I have to convert back, and that will give you your final answer. So the mathematics is easy, but wrapping your head around exactly how this power is being distributed to overcome dissipational forces plus some of the weight of the car, that was a little bit tricky. All right, so I hope this helps. Good luck on this problem.